Welcome back to our video session. In this session, we want to discuss the Little's Law. What is Little's Law? Very, very simple. As you can see in this slide, the big fonts that tells us the relationship between the inventory, the WIP as in most textbooks, uh, with the flow rate and the flow time. Okay, in a very simple equation form, Little's law expresses the count, right? The WIP, the 1, 2, 3, 4, 5 items on the conveyor belt, the WIP, work in progress, the inventory, with the product, right? As the product of the speed of flow units flowing through. How fast is it or how slow is it? Times the time required to go from entrance to exit of the process. And remember, a process can be super complicated, having irregular shape flowing here to there internally, right? As long as there's an entrance and an exit, that's all Little's law cares about, right? So the time it takes for the flow unit, the particular flow unit, to enter, meander through the internal routes, and then exit as a produced good. And that is the flow time, right? Now, you might also object, but then sometimes there are fluctuations, yeah, because one flow unit might take 1 hour and 2 minutes, another flow unit 58 minutes, and more of those fluctuations. Then what is the flow time? Well, here the red font is where we try to make sense of these fluctuating numbers. It is the average, right? All right, average over a well-defined, sensible period of time. Average of these measurements of flow time, right, multiplied by the average speed of the flow units will give us the average count, because one moment you take a photo of a snapshot of the factory, you counted 3 items, right? Another photo might be 4, another photo might be 3, another photo might be 5. Well, you just take the average of these numbers, so maybe 3 point something, 4 point something, right? And that average is the product of the average flow rate and the average flow time. So very simple equation, but big statement. Just like Einstein's equation, E equals mc squared. So simple, yet it embeds so much meaning, right, about the underlying physics. So let's take a look at the notes here, right? What are the assumptions? First, there must be steady state equilibrium, SSE, remember, right? So the FR in equals to FR out. Whatever you're feeding in on average is the rate of flow units coming out from the factory. So it has to be on a steady state. That means the average rate. Now, momentarily, there can be a bit of a jittering, right? So a little bit of a spike. You feed a little bit too much, too fast, and then the next moment better be that you have a moment of slow feeding so as to average it down. So it cannot keep rising and yet the output is steady at a constant output flow rate, right? Cannot be. So the in must be equal to out in the average sense. Average sense. So momentarily FR in is greater than FR out. Momentarily FR out is greater than FR in. Doesn't matter. It's fine, right? So long as on a sustained basis the averages don't move, they are equal to each other. Okay, fine. Or stationary, that's what we call it, right? Next is there must be a closed process boundary. So we have to draw a border line around the factory, around not necessarily the process, but has to have a boundary. So we are talking about more like a Little's law boundary. So you might have a whole factory, like I said, for example, the Toyota's factory will be 7 football fields wide, right? It cannot be managed by one supervisor. So there'll be like, let's say, 7 supervisors. So one supervisor might want to analyze its own, sub-process, that particular football field segment that belongs to this charge, and then you want to draw a little slaw bound, right? So strictly speaking, the process to Toyota, if it analyzes its own factory, has to be 7 football fields wide. But for that supervisor, can I apply Little's law? Sure. Onto my own territory, right? My own sub-process that is 1 football field wide. So you have to have a Little's law boundary. There must be a closed boundary. So that what you predict here in the Little's law equation makes sense, right? It cannot be an open boundary where, oh, I think that is included. No, this is not included, right? So there's a clear boundary, right, within which all the items, all the work in progress items are already accounted for by this equation, by this inventory here. Okay. And of course, in this boundary, there better be a clear entrance and an exit so that you have a clear FR in and a clear measurement of FR out. And you can prove, show, monitor that FR in on average is equal to FR out all the time. The WIP, right, the resulting calculation here given by flow rate times flow time will be counting the inventory or the work in progress semi-completed items, but we generally just call them inventory in academic speak, inside the process boundary. So the process here is more like Little's law is analyzing the process where we draw a sub-process around our football field that the supervisor is in charge of. Or if you only have one resource, you're a supervisor for this resource because this resource is complicated. Like, for example, the painting machine, right, of the car chassis is really huge and not so simple, even though it just paints. So you are the supervisor in charge of it, and you only have one resource. Can I analyze this resource using Little's law? Sure. So my process boundary is this resource. And incidentally, my Little's law boundary will be this process boundary, right? So WIP will count the inventory inside this boundary. The flow time measures the time for the flow unit to move through the process boundary, the Little's law boundary, right? So there's a clear definition of entrance and a clear definition of exit. It cannot be, fenceless. Anything that comes and goes are all counted. It's very difficult. So there's a clear entrance, clear exit. Applies to all distributions of inflows and outflows of processes. Any kind of distribution. For example, the FR in follows a normal distribution. That's what it means, right? So it fluctuates, right? Yeah. On average, it is 1 piece per minute, but it's sometimes 0.8 pieces per minute, 0.92 per minute, 1.1, 1.3, 1.2, right? But most of the time it is at 1 piece per minute. So the average is 1 piece. And the distribution, normally distributed. Or it can be Poisson distributed. It can be binomially distributed, and so on, right? So whatever it is, the flow rate, right, is having some sort of distribution, flow rate in, and the flow rate out can also have another kind of distribution so long as the mean is the same. Then we will have steady state. So the inflow distribution can be a bell shape, normal distribution. The outflow distribution can be a Poisson distribution, a kind of a asymmetrical distribution. Fine, so long as the mean is the same. Then Little's law applies. So long as steady state equilibrium, right? There is steady state equilibrium, and doesn't matter if the distributions are different, same, uniform, constant, strictly constant, no distribution, right? So it's like strictly maintained at 1 piece per minute, no fluctuation at all, and output is the same. So no distribution still applies, doesn't matter. All right, so those are the conditions or observations about Little's law. Now we can, of course, we should of course apply this to process, but just to illustrate, right? Let me move myself to the left a little bit. Okay, then you can see. So we have here an example that we are talking about a river where the left bank and right banks are obviously not regular, right? So some may meander a little bit more drastically than another bank, and so on and so forth, right? So you get the idea. Some segments are wider, some segments are narrower, so the water might flow faster. Whatever it is, we have this. And we like to ask a question. Calculate or estimate the amount of water in the river. Wow. So what are you thinking about? What are some ways? What are some clever ways? And of course, our way, Little's Law, right? That's what we are talking about. So how do we do it? Well, we first outline a Little's Law boundary, which happens to be exactly the bank lines, right? The river banks, right? Like that, right? So that's exactly the Little's Law boundary. Is there a clear entrance and exit? Yes, right? So we look at the, what do you call that? Tributaries, right? So the entrance here, FRA. And then the downstream, the distributaries, before it splits apart, the FR out. Yeah, so we can measure the flow rate. Is it steady state? Sure, because as the river flows, as long as it's the same season, right, the same 3 month season, any average amount of any day that you pick within this season, the summer season, let's say, right? So any day that you reasonably pick randomly, you will see river flowing gently. Yeah. So and of course it is steady state. The amount of water coming in is the amount of water going out, because short of which you either see the river gradually dry up, right? Uh, in the day it was, high tide. Uh, Evening and night, the whole river dries out, right? Then it is not steady state. Uh, or there's more water coming in than water going out, so you have flood, because it will overflow, and you will have flood, right? And so those are, of course, natural uh, climate and behavior and observations. But we are assuming a nice weather, typical day in summer where the river is flowing fine, right? Now, obviously, some rivers are very seasonal. After the summer season, it starts to dry up, right? Maybe something like that. So kind of like everyday basis, there's a gradual drop in the water level. Fine, but so long as it's so gradual that one day's time is not enough to see a sizable difference, then we'll just treat it as constant. Okay, so we have steady state. So how are we going to use the Little's Law to uh, estimate the amount of water in the river? Amount of water cannot be speed, cannot be time, so you have to be count, right? Counting the water droplets. For simplicity, let's say one water droplet is 1 milliliter. One water droplet is 1 milliliter. So we're saying how many water droplets are there inside the Little's Law boundary in the river. That's translating the original question. Yeah. And so instead of counting the left hand side directly by observation, we can do two steps on the right hand side, right? So on the right hand side, we use a meter, a water flow meter, which is easily available with good precision. We can put it here at the start to measure the water flow rate. Okay. And if you think that is too crude, you can measure this several times of the day, a few hours. You can measure it here and in the middle and at the exit, and then take the average, whatever it is, whatever sample size you feel comfortable, right? So you can sample over different locations of the river and over time just to take the average, no problem. So you have an average flow rate, right? In terms of it may be directly how many milliliters or liters per minute. Okay, so if it's 100 liters per minute, then we will need to find also the flow time. What is flow time? Flow time is the time it takes, average time it takes for a particular flow unit to go from entrance to exit. So we can drop a float, those fishing float, right? So the float is allowed to meander with the water particles, flowing all the way downstream. Sometimes there may be a small whirlpool, so it goes back and forth, right, in an unreasonable way, like lengthening the travel time, right, like that, and then going backwards, possible. So if this flow time takes 60 minutes for simplicity, right, and if you don't feel comfortable with one measurement, one sample size, then take more. Either you repeat this experiment once in the morning, once in the afternoon, once in the evening, Or you put 10 different floats and they all meander, right? Assuming they don't hit each other and then affect each other's timing. And they will just spread across the river and they will flow down, some taking longer, some taking shorter time. So you stand at the outlet there and start collecting the 10 floats. And they don't reach you all at the same time. I think you can imagine that, right? So some will arrive earlier, some will be later. So you will start the stopwatch the moment you release them, and then you quickly run or travel or drive to the out exit point here, and you start collecting them. And once you collect one, you write down the time lapse, right? So and then you collect. So you have 10 different samples, and if you repeat that 3 times in the day, then you have 30 different samples of flow time. So all you do is you average them up. Now you have two averages now, right? The average speed of travel of the water and the average time it takes for a particular water droplet to go from start to end. Multiply them together, it will be 100 liters per minute times 60 minutes. So that's 6,000 liters of water in the river. That's it, on average. This moment, it may be 5,997 liters. So we are wrong, are we? Next moment is 6,100 liters, right? We are wrong, but are we? We're talking about the average. So Little Law is talking about the average. We're not talking about moment by moment. Moment by moment, there is inequality all the time, almost. But on average basis, so long as the fluctuations are not too large, like the river flow rate is not differing by too much, flow time is not differing by too much, then your average inventory is more or less accurate, don't you think? That's the power of Little's law, right? We are not going to try to, in calculus we learn, right? Try to draw a grid, make it regular, at least at a small scale, find the easy ones, and then, and so on and so forth, right? Then do a integration and summation and whatnot. And that's the micro way, the microsurgery way. Whereas Little's law is the macro estimation way. Okay, not super accurate, but very easy to achieve a reasonably good answer. And it is used a lot of times in estimating the inventory, because inventory is money, 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 right or not? Yeah. So, and estimating inventory by counting is not so easy. Because you go inside Toyota's factory, 7 football fields wide, it's going to take you a lot of time to count. If you count, it takes a long time, and by the time you finish counting the first football field, the inventory in the second, third, fourth, fifth football fields might have changed, right? So not so accurate and not so reliable. But what you can do is to measure the flow rate, either in or out, or average them. The flow time, which is easily measurable, you just tag the chassis and then wait for it to come out. Times them together, you have a reasonably good estimate of the inventory amount in the factory. And multiply by, let's say, average semi-completed car chassis for Toyota, average amount $5,000. That number, the inventory number times $5,000, will be going into the balance sheet of Toyota, right? The inventory balance sheet. How much is it? So, and that estimate, even though it's estimate, and we don't want to be too crude in our estimates as far as money is concerned. But then in millions and millions of dollars, these estimates are going to be fairly accurate already, right? So that's good enough. So far, okay? All right. So that's for river, right? So we talk about river, but we can use the same drawing as amount of food in the body. How much food is there in terms of, say, kilograms, right? Are there in your body? It will be either by inspection, you cut yourself open and take out the stuff and then weigh. But no, we're not going to do that. We'll just take the eating speed, how many kilograms per minute per hour that you eat, times the time to output. So you might have eaten I don't know, iodine tagged food or whatnot, right? So then the moment you start chewing, we start the stopwatch, and by the time it gets excreted from your body, stop. And then we can do a multiplication applying Little's law. Your body is the Little's law boundary, right? So it will give you the inventory of food in terms of kilograms. What about the homework? The number of homework questions for lean operations, this quotes, right? Quantity of homework in progress. It will be the assignment rate. Every week or every session, I give you sometimes 5 questions, sometimes 8 questions, sometimes 6 questions, depending on the week's topics, right? But then you take the average. So that's my FR in for you. You are having an FR in or my FR out, right? Something like that. Then multiply the average time it takes for you to complete a question. Some questions takes you longer, right? So you will have to spend 20 minutes per question. Some questions you look at it, a bit of calculation and you're done. So 5 minutes. So average up maybe 12 minutes per question. Then you want multiply that by the assignment rate. Let's say 5 questions per week, right? Okay. Then your time to complete will have to be converted to week basis as well. And if you finish that fast enough, then your quantity of homework could be like 0.1 question. So very, very little homework. And because you are able to finish it fast enough. So you don't see a whole pile of stack of questions. But then if each question takes you, 1 day, including the time you get frustrated, you just have to, do other things to distract yourself and then come back, right? So yeah, because if you don't do that, you cannot continue. So that's part of the processing time. So if you do that, that contributes to your flow time. You will have then longer flow time, and your quantity of your inventory of homework questions will pile up. You'll start to see, oh, there's still a lot to go, right? Yeah. Okay, so a little bit about the implications to the business. So for that, I have to move myself back so that you see the bottom. Okay, so over here, flow rate, when it goes up in a factory setting, right? Conveyor belt, right? And we have flow rate and the flow time and then the goods on the conveyor belt. So as flow rate increases, this is what it says. Right? As flow rate increases, safe to say the profit will increase, because profit of the company is decided by the flow rate, okay? Not flow time, not inventory on the conveyor belt. Flow rate. Of these 3 variables, flow rate decides the company's profit. Higher flow rate, higher profit. Assuming, of course, the FR demand market has infinite needs for your products. That means there's no question about selling. We are not worried about selling. Of course, in real life, we do worry about selling. That's never a given assumption, right? But here we assume that suppose demand for your product is not a question. There's strong demand for any amounts of your product. Then higher the flow rate, higher the profit. Okay, and you have to be productive. You better have good machines, good tools, good for business, of course, as your profit goes up. And usually higher fixed costs. Why? Because to have good machines, talented people, skilled people, well-trained people, operators, usually higher costs, right? In terms of heavier investment in machine because it's higher performance, or higher salary payment, higher bonuses. Somewhat lower variable costs. This is a little bit subjective, all right? More occasions that we can observe lower variable costs than otherwise. That's what we are saying. So it's not a general principle, but more times than not, we can see somewhat of a reduction in variable costs. Because just imagine, if you're making a lot very quickly, right? You're moving your stuff, producing your stuff very quickly, ka-ching, 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 profit keeps coming in. You will have to buy a lot more raw materials. You will have to hire more workers, buy more machines, correct? When you buy more workers, buy more machines, you process more at the same time. So achieving a little bit, improvement in your variable cost in terms of efficiency. And when you buy raw materials in bulk, you tend to achieve some cost reduction, right, in terms of discounts or bulk purchase and all that. So of course that's not a given, you have to negotiate like Trump, right? But tends to happen most of the time. So we see. Now, flow time. We would like, all right, as a business, we would prefer flow time to be short. As flow time reduces, right, and assuming FR is constant, flow rate is constant, but if flow time is reduced, then the lower the flow time, the better. Why? Because inventory is reduced. So in business school, as you are doing now, when you're studying business subjects in business school, the advocate is lower inventory is better for business. Okay, that's the right answer, right academic answer, but not really the truth all the time in real life, right? Because sometimes we want purposely to have higher inventory, of course, at higher costs, storage costs, holding costs, right? Purchase lockup amounts of money as inventory, and so that's opportunity cost as well. But then there are times when we need that, right? Either for fear of uh, not having supplies, for national security, for various purposes. So, but then the right thing in the peacetime, in normal businesses, is that the lower the inventory, the better. So if flow rate is constant, then obviously lower flow time, lower WIP. So that's good for business. But superbly expensive to achieve by reducing flow time. That is, investments, you have to invest in super high-end machines, right? Expert consultants will know how to cut production steps in order to reduce flow time. And then your machine, from 3 machines down to 1 machine, you better have a very high-end, multi-function, and yet high capacity per function machine. So if each machine is 10,000, you're going to buy one machine that does 3 things at the same flow rate, same capacity. Do you think that machine will be still $10,000? Maybe not lesser. You might think there is synergy, so less casing, less material, so cheaper. It may be because it's so super duper, they achieve enhanced capacity, right? So you tend to not get just the same capacity, but 50% more capacity because they're integrated. Wow, right? So that combined machine will not cost you 30,000, but maybe 50,000. And if it's newly introduced in the market, then it may be 70,000 premium, right? So you see that usually it's very expensive, huh? High technology, and so you need expert consultants. So usually flow time increases over time. That means as lethargy and inertia and bad habits, malpractice, whatever it is, seep into the process. Yeah. Okay. So if you newly set up a factory, none of you has set up a factory. I must say I haven't set up a factory, but we can imagine if you set up a factory, machines, everything are bought, right? All set up, running well. Day one, very excited. Day two, very excited. Day 1,000, 3 years down, uh, it's like another working day, right? Yeah. So if the factory loses that momentum, loses that discipline, loses that sharpness in all the processing, parameters and observing all the rules, then the flow time tends to increase, right? Sometimes it's not due to bad habits of humans. Sometimes it's due to machines themselves. That the stated parameters, it takes 10 seconds to produce this. But as time goes, it becomes 11 seconds. Although it's increase of 1 second per flow unit, but you're generating millions of flow units every day, so it becomes extra 1 million seconds. That is, time wasted, right? So that extra 1 second will cause each of the flow time to be extended by 1 second. But you have multiple stages. If you have 10 such stages, and that's not incredibly large for a typical factory, 10 stages of processing, right? When you have 10 stages, each one adds 1 second, where the processing time is 10 seconds. You lengthen it by 1 second. That's like 10% increase of the flow time. one machine increases by 10%, but they're all sequential. So 10 machines will increase 10%, right, of each. If all the processing times are 10 seconds, then each one increases 1 second, you have 10 steps. Then you have increased by another 10 seconds. Well, that's a lot because it's 10%, right? We're not talking about 1 second, it's trivial, right? But because the processing time on average is 10 seconds. So 1 second of lethargy, of extension, of illness by the machine is a very big thing. So we're talking about 10 seconds. It's like if on average the processing time to paint a car is 10 hours, you increase by 10%, right? So now after 3 years of operations, machine is like a bit slower, painting slightly less eagerly, right? So it adds another 1 hour because it's 10 hours, right? Add 10%. Let's add another 1 hour. Now you get it, right? Now it's like, what? 10 hours? Now you take 11 hours to finish. Yeah, that's the kind of damage we're talking about. Over time, flow time increases. So since we know it, if you end up being a factory supervisor, better watch out for flow times gradual creeping increase. Okay? And you don't have to be a factory supervisor to experience flow time. We talked about it just now in many situations, right? Your body's digestion rate, right? The flow time, your the time to complete your homework, that's the flow time, and so on and so forth. So uh, watch out for those. WIP, as WIP decreases, right, the inventory sitting on the conveyor belt, as it decreases, the current inventory cost decreases. The cost of writing off all current inventory as in those sitting on the conveyor belt, semi-complete and all that, decreases, right? So as inventory decreases, because, for example, flow time is shorter, or simply because somehow it decreases, then the responsiveness increases. What does that mean? Responsiveness refers to a change in customers' demand. So customer already said, I want 10 pieces. Sometime later, unexpectedly, a phone call comes and sorry. Okay, so it can be sorry, I want only 5. It can be sorry, I love it, right? I want another 10 more, so 20. Either way, you are not able to respond. If you are not able to respond, then poor responsiveness. Yeah. So, but if you have very little inventory and you have high flow rate, right? So if customer doubles, well, you just produce, no problem, right? If customer cuts by half, then since your inventory sitting on the conveyor belt has to be discarded and restarted, and there's very little, then it's not a lot. You can just throw them away, right, and restart the whole batch for the customer, right? So you're not going to blame the customer. Customer says, so sorry, I wanted 10, but now after discussion, we only want 5. Would you be very angry if you have low responsiveness because you look at your inventory so much on the conveyor belt? You mean I have to throw away all these and redo everything for you? No way. You're going to scream and yell at the customer. You might even threaten to sue for the compensation. Of course, you can't get repeat business from there on. Yeah? But if your responsiveness is good, why? It's not because you say you want to be good. It's the other way around. It's because your process is engineered with having low inventory, low WIP on the conveyor belt, so that when customer, especially when they cut by half, not increase by double, right, but cut by half, you are going to look at your inventory and say, well, very little anyway, right? So you will be gently reminding the customer, oh, for you, no problem. Yeah, you'll be my long time customer. For you, anything, I'll do anything, right? So I'm so sorry that you have to write off all your inventory and restart. So sorry. I promise I won't I'll do it again. Doesn't matter. You're our long time customer, so no problem, sir. I'll do it for you, right? So you can respond very favorably to such unexpected changes. And can I say, like, pretty surely that most customers will love this kind of reaction by the supplier, right? Not even though, I mean, of course, provided you're not sabotaging or purposely doing that, then your attitude, the customer's attitude, is going to be very apologetic. But hearing that, wow, you can accommodate, should I pay you some compensation? Oh, no need. Right? I mean, imagine the happiness that the customer will have, right? So high responsiveness corresponds with typically also very good customer satisfaction level. But customer satisfaction is more like a measuring thermometer. You try to tap the satisfaction level of the customer. Responsiveness is our own ability, right? Our own engineering result uh, to to be able to have high or low responsiveness depends on our own design, our process design. In the extreme case, WIP is cut all the way down to nothing. That's the just-in-time concept that you must have heard, right? So we'll revisit just-in-time concept again in relationship with Toyota's way of manufacturing things. So zero WIP in business school, I need to stress, in business school is touted as a good thing. No inventory is the best. No semi-completed inventory is good, is the best. In the extreme, zero WIP is the best, right? Just in time. When you need that finished product, it gets delivered. When you need that raw material, supplier sends to you just in time. Of course, this demands a lot of coordination in the supply chain, right? Which is delicate, right? Already in peacetime. So when it comes to turmoil like tariff war, like U.S.-China tension, wow, right? So right now is the best time to observe and learn about supply chain reactions to regulatory changes. Best time because different supply chains in different industries will react differently, and different countries' suppliers will react differently, even when they're in the same industry. So very interesting time to watch. One more discussion on the use of Little's law in finance. And I try to repeat this river diagram here. And I want you to use your imagination a little bit by by imagining that this boundary is very virtual, right? So it is more like binding the some sort of a parameter that contains the money, the flow of the money. So let's just look at the Little's laws measure applied to financing. So the flow time for the cost to revenue, cost to revenue is going to be the inventory divided by the cost of goods sold. So the inventory, the label inventory, if you open up the balance sheet section of a company's financial statements, you will see balance sheet, right? There will be some items underneath the balance sheet. One of them will be labeled inventory. Okay, so for example, cash is another uh, item on the balance sheet. So how much cash do you have, right? And then how much inventory do you have in terms of dollars, not in terms of count, in terms of dollars. So inventory you take from the balance sheet, and the cost of goods sold, which is copied from the P&L, profit and loss statement. So there are two financial statements, balance sheet and profit and loss, produced by the company every year. Whether you're a public company or private company, you produce that. Okay, so uh, from the profit and loss statement, there is an item called cost of goods sold. The amount of dollars that we spent, right, throughout this financial year that is used for buying raw materials, purely for buying raw materials, all kinds of raw materials. Doesn't include siloing, but just the materials. So from $1 worth of raw material, that's the cost of goods sold, right? And how long does it take to turn that $1 of, you can say, investment, right? Purchase of the raw material into $1 billable $1. So that means we have sold this already to the customer, for the customer. Okay, so that's the idea here. And this is flow rate. Cost of goods sold in terms of dollar is flow rate. Why is it flow rate? I thought that's just a number of dollars from the profit and loss statement, right? Like cost of goods sold, $10,000, right? But this is divided by 1 year because P&L is always for 1 year. Balance sheet is for 1 moment, the last day of the year, 1 moment. So that doesn't count. That's like a camera snapshot. But P&L is over across 1 whole year. How much accumulated purchases? Because the company could be buying in January, buy some more in February, didn't buy in March, buy some more in April, like that, right? So over the 1 whole year, what's the accumulated total cost of goods sold, or rather the amount of money we spend on buying raw materials in order to make products, to make brand? So that is actually a flow rate. Okay, a flow rate. So the flow rate times the flow time gives us the inventory. So that's little stock. Can you see that? Okay, so this inventory divided by the flow rate is going to give us the flow time of what? Of cost to revenue. Okay, now that you understand this relationship, we can apply the same to flow time, accounts receivable. If you have studied a little bit about accounting, accounts receivable is the amount of money, right, at the end of the year. So it's on the balance sheet. At the end of the year, the amount of money sitting on the ledger where you have billed the customer, but the customer hasn't paid you. You have billed means customer knows they owe you. That means they are liable. Well, so legally, right, if you don't pay, you have a justifiable cause to sue the customer for money. So they know they need to pay you, but they haven't paid. Okay, sometimes they are just too slow because it's an MNC, right? Sometimes they purposely don't pay. Okay, that's a different issue. But as accounting goes, we don't care. All these go under accounts receivable. So let me ask you, a company with high accounts receivable is good or bad? Probably bad. And of course, for accountants, they divide up this money. If it's large amounts, they will categorize them, right? So those that are still within 30 days, which is quite usual, right? You don't expect the customer to immediately pay now, right? The next day, right? Pay within 24 hours, seldom. So within 30 days, sometimes even within 7 days, within 14 days, within 30 days, and beyond 30 days, hopeless, right? Or beyond 3 months, hopeless. Right? So that's accountant's business. But AR, just the lump sum of all the monies unpaid divided by the revenue. This you take from the P&L. Remember, across the whole year, how much money have we earned from our customers for the company? So that is a flow rate in, because money coming into our company, right? And the amount of monies that are owed to us as inventory. Okay, so that division, that ratio gives us the flow time of AR. What is that? Time taken to collect $1 from customer from invoice to cash. From invoice to cash. Invoice means we tell the customer through a paper or email, you owe us $10,000. To cash means have receipt. Actually, to cash doesn't mean to literally cash. It can just mean, liquid payments, right? Fulfilling the liability. So we tell customer you pay us $10,000, then we wait. That's the flow time until we get the $10,000, right? The money is fully transferred. That is the flow time. So let me ask you, flow time AR, longer the better or shorter the better? Of course, shorter. Zero even better, right? Time taken to collect $1, right? So 0 time. The customer pays immediately. What? I owe you? Okay, now pay, right? But in real life, they tend to extend to infinity, right? Some bad business ethics people, companies will do that as a form of funding, because they have enjoyed the goods and services. I have to pay you $10,000. Sorry, I didn't know that. Let me check. So they take a long time and whatnot, right? So this is a measure of that. And now it's easier, right? Full time for AP. What's AP? Kind of similar to AR, but now the roles are reversed. AR is our customers have yet to pay us. AP is accounts payable. We are now the customers to our supplier. The amount of money that we have been told to pay to the supplier sends us a bill, $5,000, right? And we say, oh, is it? I owe you $5,000. I didn't know that. Let me check, right? So the other way around now. So we say flow time of accounts payable. And we use accounts payable. There's another entry in balance sheet. Just look for it. There's an accounts payable, right? So accounts payable, how much money? Divide by normally cost of goods sold under the P&L, right? So the idea is raw materials for suppliers only, okay? But sometimes for some companies, the cost of goods sold could have included, right, by mistake or by accounting practice, certain overtime salaries, for example. Not the usual committed salary, but special payment salary, or like hiring temporary staff to quickly finish it up. But otherwise, this staff is not our staff, just some temp worker, right? So maybe through accounting misunderstanding, or they it's a one-off thing, so it's okay accounting wise, but they just do a special note. So they put under cost of goods sold, which is kind of not wrong. But here, what we are trying to do is to account for just the input material to our process. Remember, we're not accountant. We're just trying to reuse the accounting results, the financial statements, to measure the financial health of our operations, not the company. So in those cases, it will not be the pure total cost of goods sold, but we will just dissect out the cost of goods sold to minus out the salary part. Okay, so because it's more like a service payment rather than a material. So cost of goods sold, raw materials, purchase parts, right? And any other things that are hardware, raw materials that go into the input, right? Except services, except temp salaries, like special overtime or whatnot. Okay, so out, right? So that's why you see more terms. But in general, it's just cost of goods sold, similar to this. So that will be our FT of accounts payable. It is the time taken for us to pay $1 to our supplier. Question to you. The longer the FT AP, the better or worse for the company? Well, longer tends to be a bit better, so long as there are no collateral damage. So you don't try to drag until so long that the supplier just don't talk to you but sends you a legal letter demand for payment plus compensation for interest loss plus penalty for this and that and so on and so forth, right? So that will be problematic. Or there's no legal letter, but then supplier keeps calling you, you keep saying, oh, is it? I didn't know I have to pay $5,000, right? So you keep delaying. Who is going to be happy with doing business with you right now? Yeah. So word will spread, even though you're going to like renege on this supplier and then keep the $5,000 ill-gotten gains. I hope you won't. But if you do that, then words will spread, right? And then no other suppliers will work. So if it is longer than industrial practice, it's kind of good. If on average, uh, businesses operating in your industry and sector has an FTAP of 7 days. Maybe it's industrial practice, they're going to quickly pay. But you have a 14-day FTAP. So that means good. You are able to sustain that kind of flow time with your suppliers. So in some sense, suppliers are funding your operations. They are able to not take your money and let you take the raw materials. So that is a good thing. That is a good thing, right? Because suppliers are willingly, so they understand, they are willing to fund you for that. And that sometimes happens. Like Toyota may supply certain raw materials to some of its suppliers. So it's the other way around. Suppliers supply to Toyota, but then Toyota may, send certain supplies to their supplier. For example, the engine, right? So the engine maker or the sofa, the car seats, right, maker might require raw materials from Toyota, okay, because Toyota insists on using this kind of leather, right? But I'll give you, but you help me make the car seats. So if that's the case, Toyota may say, okay, go ahead, take the leather first and go and do your stuff, right? Uh, Supplier will say, but then I'm going to pay you. Don't worry about it. All right, we'll extend this to 60 days. So take your time. Don't worry. So that is basically Toyota helping, without outright giving money, but then it's helping because supplier now doesn't have to worry about forking out extra cash to buy that, raw material settings and the ladders and all that stuff, right? So it's a form of assistance. Yeah. Cash to cash cycle. What does it mean? First of all, I take $1 from the company's money to buy raw material. Okay, so $1 now gone, converted to raw material like dough, right, to make bread for sale. But how long does it take for that $1 purchase of dough and flour and all that for it to be converted to $1.50 as profit? Correct or not? Yeah, to $1 of cash received from customer. So I don't know. In our analysis, we don't care whether $1 gets turned into $1.20 or $1.50 or 80 cents at a loss, right? We don't care, but we get back the conversion again. That means $1 in. When do we get back the $1 out, or 80 cents out, or $1.50 out? So that's the question. Cash to cash cycle. Okay, so it's given by this formula, just subtracting, minusing some of the flow times. But question to you: this number, cash to cash cycle, if it's longer, is it better for the company, or shorter, the better for the company? Yes. $1 in, how long do I see the $1 out, or $1.50 or 80 cents out? Of course, shorter the better, yeah. So that we can see the result. If your business is such that $1 in ultimately will result in a loss, 80 cents, you get back only 80 cents, right? Then no choice. You better get back the 80 cents and try to reinvest some more, perhaps in the same business or other business. At least you get back the 80 cents. So you don't want to keep the 80 cents inside. But of course, if it is $1 resulting in $2, so a profit of 100%, then you want that $2 to quickly buy more flour to pump in so that you can get $2 in and then $4 out, right? So that speed of this will be the cycle time is shorter, means the speed of this conversion is much higher. Therefore, your profit intake is at a much higher speed. Inventory turnover ratio. That means how many times within a year do you replace the inventory? So then just imagine you have like 100 stacks of flour, right, to make bread. Throughout the year, how many times do you make into bread, sell out, then buy some more, then make into bread, then sell out, then buy some more, and like that? So how many times? How many times do you do that? Now, number one, businesses don't keep on used up their raw materials, then buy. They halfway through will buy again, correct? So once I use until left 20% or something, I will start buying already. So you don't actually see the raw materials, the flour, let's say, right, go all the way down to zero, then gets replenished. You don't normally see that. I mean, it's easier to imagine what this term inventory turnover ratio means by saying 100 all the way down to zero, empty out, then replace with 100 all the way down to zero. How many times of 100 to 0 do we see in a year? So that's easier to understand. But then in real life, it's a lot more complicated, right? Because 100 to 20, then you get replaced. The next cycle, maybe 100 to 50, then gets replaced, and so on. So inventory turnover ratio. That's number one. Number two, this number, the higher, the better or worse for the company. Number of times the company's average inventory is emptied out and replenished. Now, of course, assuming demand is not a problem, whatever you make gets sold and turned into profit, right? Then the more times you turn over your inventory, average is 100%, right? So sometimes you have more inventory, sometimes you have less inventory. Maybe over the down season you have less inventory, right? The high season, near festive season, you make more bread, you have higher inventory. So we're talking about average inventory. How many times of the average inventory do you flip throughout the year? Now, this flipping, this empty out, then top out again, then empty out, then top out again. The higher number of turns you have, obviously, more money coming in, right? Because assuming, of course, demand is not a problem. So the higher the ratio, the better. Okay, all right. So some auditors, accountants, they look at this, especially for example, if you are doing retail sales, the turnover ratio is rather sensitive, right or not? Yeah. So if you open a bread shop selling to retail people, and every day your turnover ratio is 0.5. What does that mean? Every 2 days, then you completely empty out your average inventory. So it's a bit slow. If that is more or less that ratio for various bakery shops in Singapore, right, in roughly the same place like Heartland malls and all that, then fine. But then if other bakery shops in similar kind of heartland, similar traffic areas, their turnover ratio is 3 times a day. Or one day they turn over their inventory 3 times. All right, then they are nice. But you may say that, wait, my average inventory is a lot, that shop, how can you compare? Because that shop's average is very little. Well, they are smart. They don't put so much money in their inventory so that they have lesser inventory, they turn over 3 times. It's smarter than having a lot of inventory and then 2 days and you turn over 1 time because your money is locked up in the average inventory. Right now, yeah. So whatever it is, this ratio is like net everything. What's your heartbeat, right? How fast is your heart beating? Then you don't say, oh, that guy has a small heart, but I have a big heart. That's why I beat slower. It's okay. You don't do that, but it's more like how is your heart beating, right? So if it's beating faster, right, it's supposed to be healthier. Well, it's not true for our hearts, but then if it's too low, then it's no good. If it's uh, too high is no good. But here, inventory turnover, the higher the better. But if it's too high, way higher than industry average for your sector, for your business, something fishy is going on, right? Yeah, are you doing something illegal? Are you masquerading something else with your product, something like that? So again, it will raise alert to accountants. Okay, so what you need to do in terms of calculation, I've already flagged out the items. For PL, go to the profit and loss financial statement. For BS, go to the balance sheet statement. If you're ever asked these questions for Little's Law, related to not the finance, as in like I want to have higher ROI for finance, where should I invest and that kind of thing. That's pure finance. When we say Little's Law in finance, we are talking about applying Little's Law in terms of estimating, right? It's the through the finance and dollars and cents, what's the health of our operations. Now, how this will help you is perhaps to, if you invest in stock market, right, and the particular stock that you are investing in has got to do with manufacturing, logistics, retail, Sheng Song, that's a retail. So they will buy inventory. So inventory management is very important to the success and failure of these kind of companies. You mismanage your inventory, it's basically toying with the health of the company. So very, very important to look at those numbers. So how do you analyze? Then you want to look at these numbers. Okay, and then a few things also that these numbers are in dollars. So you extract out dollars, like inventory from the balance sheet. They don't tell you vegetable has how many pieces, and assuming one piece is how much, it is no. You don't get the quantity. You get the dollars. And what's so in a way problematic with dollars is that um, the dollars don't necessarily tell you the superiority or importance of the inventory. So, for example, if I'm dealing with second-hand computer parts, right, and I have a huge 500 pieces of the old Intel motherboard using 486. You might not even know what that is. Google it, right? 486 is like the umpteenth generation ago. Very, very slow CPU relative to today's standard, but nobody wants, right? But I have them. They're all running fine. They can be booted up. They can run MS-DOS. Okay. That inventory has $0 because nobody wants to buy. So the accountant will attach a $0 inventory to that 500 pieces. But then, is it possible that I find some way to monetize them? Maybe to sell them as hobby electronics? Maybe to sell them as rare electronic boards and therefore commands a premium, right? And so on and so forth. And who knows, right? So it's not actually zero. In unit quantity, it's 500. But then as far as accountants are concerned, when you extract out from the balance sheet, $0. So it might not even be mentioned. It might not be even be included. So the potential of this company becomes not reflected out from the financial statements. Just so you understand and be careful about directly equating the dollar with the actual operation quantities. So that's all I have to say for this slide. Thank you and see you in the next session.